All right, welcome everybody to the OpenXLA community meeting. This is the October rendition. We have two amazing presentations for you today. They're both external presentations. I'm going to hand it over to Jasper very quickly, but before I do that, just want to remind everybody that if you've gotten the email last week about OpenXLA Dev Lab, yes, it's happening again, back by popular demand. It's happening November 14th here on the Google campus. In Sunnyvale. And so please do RSVP. I sent out the link to the RSVP form in the email that I sent out last night. So please go ahead and make sure you RSVP to that. And then we'll go back and talk a little bit more about it towards the end of the meeting. But without further ado, I want to turn it over to Casper to talk about all the great work that he's done. Casper, over to you.
Cool. Awesome. So hi, everyone. I'm Casper. I'm here to basically introduce you to a small hobby project I've been working on, which is converting StableHLO into CoreML, so I could get some JAX models running on my iPhone. So if you go on the next slide. Yeah, basically the motivation was that I've been having fun with some models, writing them in JAX, but then I wanted to make some iPhone apps and wanted to get it running with the accelerated hardware on the phone, and using sort of the conventional translations paths turned out to be a bit difficult, which I will get into. So if you go to the next slide again. So today, if you have a JAX model and you want to get it running on your phone, what you basically have to do is to go through TensorFlow, because Apple has this quite nice open source tool called CoreML tools, which can take either a TensorFlow model or a PyTorch model. It will then convert it to what they call their model intermediate language, which then again gets saved as a CoreML file that you can then import into Xcode and run on your phone directly. So if you go to the next slide again, what I started out doing was to use the exporting functionality of JAX to get the TensorFlow model and then basically use this tooling. There were a few things in this approach I didn't really like too much. First of all, I needed a dependency on TensorFlow. And second of all, this basically requires two translation steps that can possibly go wrong, one from JAX to TensorFlow and then from TensorFlow to MIL. And I hit a few bugs doing this, which was quite annoying to debug. So I thought, okay, maybe there's a simpler world here to, like, given StableHLO is an intermediate representation and MIL is as well, I thought that, okay, maybe it's easy to just translate it directly. So if you go to the next slide again, what I basically tried, like in this project, was to make a front end to this CoreML tools repository framework, such that it can operate directly on a StableHLO module. So if you go to the next slide again, let's maybe just briefly talk about what is this model intermediate language even. So it's some language defined by Apple. Fortunately, they have documented it all and put it online. So it basically consists of a bit resemblance to StableHLO, I guess. You have a list of operations, and then you can have functions. So the main function is where you sort of usually enter the program. And I just put an example here so you can get a sense of it. The program takes two arguments. You get the shapes, you get the data types. In this case, it just does a single operation, which is a matrix multiplication, and then it returns the results. But you can have, as many operations you want to in this function. If you go to the next slide again. So obviously, the operations in MIL is not one-to-one compatible with the ones you find in StableHLO. So there's some amount of translation needed between the two. And also, if you look at the sort of more fundamental structure of the language, then like it does have while loops. It also have conditional execution, but it does not have function calls. So even though it had like the concept of a function, you cannot call a different function from the function you're in. So every time we see, or I see a function call, I need to basically inline it when I do the translation. If you go to the next slide again, then I implemented basically this conversion then in this Python file. The CoreML tools is written in Python, which is just why I picked that. And this is kind of a rough list of the operations I have implemented so far. It is what was required to get my models I was interested in working. And some of the operations I have implemented have some limitations. For example, the convolution operation, I made some assumptions about the batching dimension that the operation is performed over. And also, I have a bunch of limitations regarding the data types I support. I just support ordinary floating points now. And if you go to the next slide again, then yeah, just quickly about how you actually use this. So first of all, you need the Python package itself, which is called StableHLO CoreML experimental right now. It will also pull in the CoreML tools. And then the last two packages are just for the JAX export to StableHLO. So if you go to the next slide again, I just put in a small example of how you actually do this. So this is the JAX side. You have some JAX function. In this case, very simple. It just does a matrix multiplication, more or less that's batched. Then you call, like you say, what shapes do you want? And you call the export function in JAX. And then you get the XLO module and you can print it out. So if you go to the next slide again, you get something here that you're probably more familiar with than I am. But yeah, it's basically, yeah, you get the arguments and then the dot general operation, and then you return the result. So if you go to the next slide again, then given this StableHLO model or module, then first of all, you can now use this project. That's the line in the bold, or in bold in this code. You call the convert function, and it will take this StableHLO code and convert it to the corresponding mill operations. And then the next step is to call the ct.convert function, which is a function in the CoreML tools library that will create the actual CoreML model. And once you have that, you can either save it to a file on your disk and import it to Xcode, or as in this case, I just print out the instructions I generate. So if you go to the next slide again, this is the corresponding mill program for the StableHLO or the JAX function. And you can see it's very similar in this case. I think the main two differences is that CoreML tools does some optimization where it converts your inputs to floating point 16, and it does the 16 to 32 conversion again in the end. And then you can see the dot general operation was changed to a matmul operation, which is sort of the corresponding thing in CoreML. So if you go to the next slide again, then yeah, so obviously this has sort of been a hobby project, so I haven't done any formal testing or evaluation compared to the current two front ends, being PyTorch and TensorFlow. Could easily imagine doing some benchmarks to see how it performs. I only implemented a subset of all operations. I think to get like full API compatibility with StableHLO, some work would be needed on the Apple side to basically expose some more operations, or at least make them a bit more familiar. But for most cases, it's quite possible to do this mapping. Currently, it only works on iOS 18 simply because of the way I implemented this .general operation. Then, like, I only focused on inference basically, so you cannot do training using this on your device, but you can run your model with the trained weights. And then one very interesting thing I would kind of want to try, but I haven't gotten around to, would be to use all of the StableHLO tooling to take a TensorFlow model and a PyTorch model, convert it to StableHLO, and then use this translation step to go to CoreML. I think that would have two potential big benefits. One is that it could reduce the code in CoreML tools quite a bit. And also, it would serve as a great basis for running benchmarks for seeing how efficient this translation step is. Yeah, so if you go to the next slide again, that's basically what I had to say in the presentation. If you have any comments, questions, or ideas, feel free to reach out or send PRs. If you want to get in touch with me, either in the Discord chat, I'm there, I'm called Casper, or otherwise my email is there on the screen as well. So yeah, thanks all.
Sorry, I was muted. Any questions?
Oh, good. Yeah, chime in with a quick note and a quick question. The TensorFlow and PyTorch experiments you're mentioning, those should hopefully be super easy. We try to have very similar conversion to StableHLO APIs in every framework, so I can ping you with those afterwards.
Yeah, that would be great. I gave it a very, very quick go, but I failed to run the thing because it didn't have a proper runtime. But yeah, if you have some resources, definitely.
Was this the PyTorch one? You might have posted about this on Discord.
Yeah, I think so.
Okay, cool. Yeah, I added some people to the Discord from the TorchXLA side, so we should get that one resolved pretty easily. And my question was, you mentioned that you had some target models that you were working on this stuff. So I'm just curious, like, what did you end up getting working with this?
Yeah, so I've been experimenting with two different models. One has been given an audio file, basically say which notes are you playing at which time, so basically transcribe your piano, whatever. And then the other one was, I'm still experimenting with this, but basically it's kind of like a diffusion model that tries to clean up audio. So if you have a person speaking and a lot of background noise, I'm trying to basically separate the conversation out in a clean audio track and doing it in real time on the device. Trying to help my dad a bit, but let's see if I ever get it working.
Very cool.
All right, so moving on. Steve, I'm going to let you share your screen.
Thank you. All right. First of all, thank you, everybody, for having me. Thank you, Kevin, for suggesting it. Thank you, Aditi, for the warm welcome. And great job, Casper. I'd love to look into that. I've been looking into that myself. So, anyways, so yeah, I'd like to talk to you guys today about ZML, which is an ML framework that is based, on Zig, most notably, targeted at inference. So the first thing is, why do we need, a new framework to do ML? Well, the issue we faced as operators is that everything is, built for training, essentially, and not so much for like production, so inference. So what we find is that, research mostly is making one of something. Training, we consider it to be research. More is better. We also incentivize fast iterations. That's why Python is a great choice for that. But on the inference side, well, it's production. We run these things billions of times, so less is actually better. Whatever metric you want to use, we want predictable latency, and for that, it's not so good of a choice, or it can, essentially bite you. For now, all the tooling around, AI, ML, etc., is built around Python. So it's most definitely, reusing training infrastructure and training code, etc., to run these workloads. So I mean, it's good and all. I love that. But I've been bitten, way too much for like, sorry, yeah, way too much by these, in the past. So essentially, who are we talking to? Well, the backend engineers. And so what do we want, right? So first thing, we want to run on any accelerator possible. We want to compile the model. We want static typing, cross-compiling, sandboxing, and all, the like. And this is essentially why we build ZML. So hopefully you will like my animation skills. And so what ZML is essentially is built around these 4 pillars, Zig, MNIR, OpenXLA, and Bazel. The idea is that, essentially we use Zig as the front-end language to generate, StableHLO, which we send to the compiler through PGRT. So we actually essentially load PGRT artifacts. We use also Bazel as the orchestrator in the build system to essentially achieve a few things I will show you a bit later. Probably the first important thing to note is that it is inference only. We may do a bit of training in the future, but we have, not many incentives to do so at the moment. We're very, very opinionated about inference. We use Zig, the Zig language as the front end. So there's actually 0 Python in our stack. Or if there is, it's way hidden. Nobody has to deal with it. We strongly incentivize modular code, which means a strong focus on maintainability as opposed to just writing the models. So how does it look? Well, it looks like this. This is a sample, MNIST implementation. You may recognize a few things, but probably the most important are, the way you define the tensor and the way you define the forward function. So it feels very high level. We use that to generate the IR. The module format you see is actually the one used by, in this case, the torch weights, tensor stored on disk. So we actually have a torch loader without Python. Which was a bit of a journey too. But it's essentially a complete, MNIST model from, the flattening of the input, to the array to, actually selecting the actual activation. So we have a few cool things also with respect to, I would say, as ML frameworks go. Probably the most notable one is access tagging, which are named in PyTorch name tensors. So we actually bend, Zig, the compilation time properties of Zig to enable a cool syntax. The cool thing, though, is that we propagate this information to StableHLO. So what that means is that we actually need much less, formatting of the tensor, transpose, reshapes, etc. Because we can just, be very explicit because we have now introduced semantics to the axes as opposed to just numbers, right? So ultimately, units mad meal, right? When you can have dot and and tagging. So this is what it looks like. This is a small example of essentially making a shape and giving it names. And then this is regular tagging stuff. The very cool thing is that in this case, this is a mad meal. These matrices are not compatible, but we don't care. We just give, which axis we want to run on. So it feels very high level. We have much less transpose, formatting, etc. because of that. And actually, so you can see the thing. And this is actually our very naive SDPA implementation, which ultimately, resumes to this. Meaning, these two dots, so there's no transpose in that code except at the end because some of them require that, but we essentially run, dot like this, and that's it. The cool thing for us is that we do away with all the bookkeeping and the formatting of tensors prior to sending them to the IR. And we found that essentially, these operations were pushing semantics anyway. So instead of requiring, let's say, 4 dimensions for an SDPA, we actually only require, tags, and we operate only on tags. Now, there's another component to that, which is Bazel. And Bazel is essentially our orchestration tool and system. We use it to provide a few nice things to our users. The first one is cross-compiling, so essentially generating Linux, binaries completely self-contained from your Mac, let's say. Sandboxing and trimming the runtimes. So in this case, if you enable a ZML model to run with CUDA, we actually download, well, the build will actually download and repackage CUDA, which actually in this case reduces to about 10% of its original size. So it matters in terms of also code start speed. We actually are able to build self-deployable archives, OCI images, and even Kubernetes deployments. And the idea is that because we sandbox the runtimes, we can actually couple the code we generate to how it's going to run. So there's no essentially CUDA version mismatch. So this is a thing of the past. Because we know at build time, which version of CUDA we're using, how it's going to run, and also what can we leverage from that, right? And so there are many such cases. I'm not lacking memes for that. Probably the most important part is that we don't need provisioning at all. We actually, run our models on machines that have 0 CUDA, 0 ROCm, 0 whatever. And that's the important part ultimately. So this is what it looks like. Classical MNIST. So you essentially just enable the runtime and everything is done for you. The cool thing, though, my favorite thing, is that you can build cross-platform, cross-compiling binaries, which run on any platforms that you chose at the build time. So you can have the same binary running on TPU, on NVIDIA, on AMD. And this code would actually build a Docker container and push it on the Docker registry. So fully on my MacBook, right? No whatever. This is the only thing I need to do. So we've been live for about 3 weeks now. So please, start us. We had a pretty good launch. We're very happy about it. And I would say, try us today. This is, essentially the only things you need to do, whatever platform you want to use. If you need to do it more, there's a problem, ping me and I will fix it. But yeah, this is ultimately what, the workflow we use whenever we have a new machine, completely blank. We only do these commands and it runs every single time. So that's it. Thank you very much. So please, try it. Would love to get your feedback.
Oh my gosh, this is awesome. Anybody have any questions?
Just to add, Steve, that's a great presentation. Thanks for sharing this great story. So could you describe your experience while setting up OpenXLA and PGRT? Like, did you encounter any significant obstacles during the process?
I mean, mostly good. Probably the most impressive thing to me was StableHLO. I would say the balance of the IR is, to me, probably one of the reasons we can say to everybody that we have cross-chip compatibility without compromise. This is, and what's coming up also, composite operations and so on. So it was mostly painless. There were a few things related to essentially the builds, but nothing, major. Probably there's a lot also of legacy Basel infrastructure in XLA that we try and run I would say the more recent version of Basel. So sometimes it was a bit hit or miss, but nothing major. Probably the number one thing I would fix if I could when I had time today would be to remove the dependencies of. So I would split essentially generating StableHLO and transforming StableHLO into 2 targets. So right now, when you actually run, these things, you will compile lineage and all the transforms, etc., because they're used by StableHLO. Whereas we don't really need them because we only generate it. We try and also build with StableHLO, right? The CAPI. So this is where most of the time goes when you actually do a first run. But it was mostly painless. Obviously, I would say the implementations vary. Some are better than others, but so far we've been very happy. We had a few problems on AMD, but nothing, that it took us a while, but now that it's done, it's pretty much okay. We do have, though, to host our own PGRT built artifacts. We used to take them from PyTorch, from PyPy wheels, the shared object. But now we just build them because we want to know, which version of OpenXLA we're using, and NXLA, of course, we're using. And there was the array transition in StableHLO earlier in the year that was somewhat shaky. But other than that, pretty good, I would say. Pretty good. We're very happy with our choices so far.
Thanks for sharing. And feel free to come up with any other feedback. We'll be happy to address them.
Sure. Thank you.
Jessica?
Yeah, I just have one quick question. Which AMD GPU, the MI like 300?
All of them we could find. We tested on, so consumer GPU, 6000 series and 7000 series for consumer on AMD. And on, I would say, professional, we tested on MI200, MI210, and MI300.
Cool, thank you.
But anything we could find, we would test on. We have, so it's not in the presentation, but we actually have very cool tricks also how to do bytecode selection at the GPU level. So say if you're going to ship with AMD, you may not, or an let's say MI300, you may not want MI200 bytecode into your image. And that actually divides the size of the image by 5. So that's significant. So it's another flag you can use. These are basal flags. So they're namespaced.
Thank you.
You've got one more question, Jendad?
Thanks. I'm going to try and keep this brief. So you mentioned that you don't need ROCm or CUDA on the system. Could you elaborate how that works? Like, are you, because I'm from AMD, I'm going to speak to ROCm. So are you packaging the entire runtime into the binary? How does that work?
So not the runtime, but part of it, roughly 10% with respect to size. So ROCm is an interesting thing because the base ROCm image is 36 gigabytes. So that is, a chunky. We actually turned down into about 3 gigabytes. So we essentially sandbox only the things that are needed at runtime, down to the file level, and sometimes even down to the bytecode level in the case of GPU bytecode. By default, we integrate them all, but if you want to get probably more precise, let's say in your deployment, we also allow you to just say, hey, I want MI300 bytecode only, right? So, and compressed, it's about, it's about 1 gigabyte compressed. And also it's quite, significant too, because, if we look back at, this use case, the archive, if you try and run that command, it will generate a ZSTD archive and not a gzip archive. So that adds a lot because we go from, in the case of CUDA, from about 8 minutes to about 20 seconds in terms of unpacking. And so this actually is propagated into the Docker image. So if you have the STD Docker image trimmed with our stuff, packed with ZSTD, you go from 5 to 10 minutes of just Docker pool to like 20 seconds.
Okay, fantastic. Thank you.
So I know we're 2 minutes over, but thank you, everybody. I'm just going to post the link to the OpenXLA DevLab RSVP form. So please fill that out. It just helps. It's just from a planning standpoint for us on the back end. But if you can do that by tomorrow, I'd really appreciate it. If you don't know, then just let us know. Just reach out so we can just incorporate that into the planning. Okay. Thank you, everybody. This was absolutely amazing. Thank you, Steve. Thank you, Casper. You guys are awesome. Love it. All right.
Thank you.
Bye.
Thanks for having us. Thank you all.
Of course. Bye.